Okay, good morning. So today we're going to start probability. So what's kind of confusing is we're going to talk about probability throughout the rest of the course, but this is the only section where we explicitly talk about how probabilities behave. Okay, and so it's kind of a separate section from the rest of the course, even though we will talk about probabilities later as well, but this is kind of its own thing. So what's confusing is, remember I told you they revamped the textbook, and so they kind of split up and made more chapters. That's great. Kind of same material, but different breakup. And so it used to be chapter 2, but now it's chapter 3. And that's okay. But it gets confusing because all my stuff is labeled chapter 2. And so I called it chapter 3. I don't know what's more confusing or less confusing, but I'll just bring this in here. So I just posted these this morning. Sorry, it completely slipped my mind to post the notes. Sorry about that. So it'll be all new to you unless you kind of flip through the textbook a little bit. Okay, and so here, chapter 2, it's now chapter 3, but it's the same material. Okay, so we don't have class on Thursday, so maybe I should write those kind of housekeeping notes down first. Forgot, right? Because well, it used to just be orange shirt day, so I've got my fancy orange shirt. Because when else am I supposed to show it off? Right, and so, but now it's our stat holiday, so no classes on Thursday, right? No classes on Thursday. So what I decided to do was, because I have a video of this chapter for Friday, just to give you guys a little bit of a break, because I don't know about you guys, but for me, things are getting a little bit hectic. Things are getting a little crazy. And so it might be nice to have kind of your own time. So for Friday, what I want you to do is I want you to watch the remainder of, well, it's the old chapter 2 video, or now chapter 3. And I'll show you where I posted it on Moodle. Because we're going to make a dent in it today, and then I'll have a look. I'll go back and I'll check and kind of tell you which point you can start watching. But also in the same breath, if you have a lot of stuff going on today, it's totally fine if you just want to watch that video on your own time. Like I said, I know things are getting kind of a little bit busy, right, with school. So if you feel like you should just watch the video at some other time, or if that would be better for you, then that's totally fine. I get it. So I posted the video on our Moodle page. Let me just sign in here. Come on. So here in week 4, kind of did a quick update. No, so the video is replacing Friday's lecture. So you can just watch it on your own time, whenever works for you. Have a little time on Friday morning for yourself. Step 230 tests or assignments. I'll get you to clarify that. But in the meantime, I'm just going to take a screenshot here. Done, save, and bring it in here. Okay. So here, and maybe I'll zoom in. Okay. Hey, I didn't switch up my microphone, but I find that it catches my voice pretty well when it's far away too. But anyways, nice to have it closer. So today we're going to work through the old chapter 2, which is now exactly. Yeah. So the deal is no lecture Thursday or Friday, but you are going to watch the remainder of this video here. Okay. And so exactly. So some self-study, just to give you a little bit of, well, not really freedom. You still have to spend the time, but it's on your own time whenever it works for you. Okay. So, all right. And what I decided, because I'll try to do that before the long weekend as well, or long weekends. So I'll try to do it when things line up. Okay, so we will start. So we will cover the beginning of this today. But like I said, this video that I posted, right? If you've got something more important to do this morning, then it's totally fine if you just watch the entire recording. And I posted the notes that go with the recording here as well. So if you just want to do that this week, that's totally fine. We're just going to go through the beginning of it together. And then what I want you to do is just watch the remainder. And I'll put the kind of the minute to start at once we finish. I will update with the minute to start at. Okay. Right. No lecture on Friday. Just watch the video sometime before Tuesday. Low pressure, high pressure, maybe. I don't know. Depends on what you like. You can watch it in double time. All right. Okay, so I'm going to be calling it chapter 2 in that old video, of course, because it used to be chapter 2, but it's all the same chapter. Okay, so hopefully that's clear. If it's not, let me know, because I do want to make sure that you know that you have Friday morning free. Okay, so what we're going to start is probability theory. So like I said, this is only awesome. This is the only section that I'll call probability. And what we're doing here is we're just building up some rules that we can apply to probability situations. And so all of statistics hinges on probabilities. And usually when I was doing my master's, people would say, oh, what are you doing your master's in? And I would say statistics. And they would ask me, what's the probability of being hit by a car? I don't know. Why would I know that? That's not what statistics is. It is the study of probability, right? So how do the probabilities affect, how things happen, or rather, how do things happening affect the probabilities? Yeah, so insurance companies, I really wanted to be an actuary for a long time. So they work for a lot of insurance companies, and they calculate risk, right? And so that's all probability. And I think the first exam, then I started teaching, and I love teaching more. So, but I think the first actuarial exam is on probability, pretty sure. And so it would just be deeper into this stuff. Okay. So let's talk about probability. So yeah, there's the survival rate, but usually they attach a financial aspect to it as well. So there's like financial risk, right? To them as a company by insuring you, but that relies on the survival rate. So it's this whole big field, very fancy, and you could make a lot of money in it, right? That was what was appealing mostly. But here I am teaching instead, but it's way more fun. Okay, so by definition, yeah, the probability of an outcome is the proportion of times the outcome would occur if we observed the random process, and I'll talk about a random process here, an infinite number of times. So technically, this is what a probability is, right? That doesn't really mean anything to us right now, but a random process is any process that yields a random result. So if you head into it and you know what's going to happen, well, that's not a random process, right? So a random process is things like flipping a coin, pulling a card from a deck of cards. A well-shuffled deck of cards is assumed. You roll a die, right? Things, basically anything casino related, right, is going to be a random process, okay? And so the probability stems from thinking about if the random process was observed an infinite number of times, which means that if you flipped a coin an infinite number of times, right, that's where we get that kind of intuitive probability of 50-50 split, right? It also comes from there being two possible outcomes, right? And so there's that kind of, we understand intuitively that because there are two equally likely, or equilikely it's called, but I like to emphasize that it just means equally likely. So outcomes, then we take the probability of 100% and we split it in half and each of them gets some, right? Same thing for rolling a die, 1 in 6, because there are 6 possible outcomes, right? But technically, a probability is if you observed the random process an infinite number of times. That's where, yeah, the limit would go to 1/2 or 1/6 or whatever. Okay? There are random processes where the probabilities are not equally split up, right? It could still be random, but it's not equal. So we'll kind of build up to that. But for now, right, if there are 2 possible outcomes, you just split the probability in half. One thing that I do want to highlight here is that we use some terminology. Probability is the same as a proportion, okay? And if you multiply it by 100, then you get a percentage, right? So that's why I have approximately equal here, but these 3 terms all mean the same things, okay? And so we use these 3 terms interchangeably, okay? So a question might ask you for the probability of something. It might ask you for the proportion of outcomes that satisfy some criteria, or it might ask you for the percentage, right? And so the percentage you'd have to multiply by 100, but for a proportion or a probability, you would just keep the decimal value. Okay. So a percentage is a probability times 100%, right? And so if it asks for a percentage, you would have to adjust that by multiplying by 100. Okay. All right. So what we can do is we can talk about all possible outcomes. right? So if you roll a die, a 6-sided die, then the possible outcomes are 1, 2, 3, 4, 5, or 6, right? If you flip a coin, it's either heads or tails. For us, I know it can happen that it lands on its side, right? We're not going to consider that outcome. And it's usually ignored. You could look at it, but the probability of it happening is so small that we ignore it. Okay, so if you want to be proper, fine, but we're going to ignore it. Okay. So like I said, let's get all of this in here. We're always going to have a list of possible outcomes. Now, the thing is, only one of those possible outcomes is going to happen, right? So each random process has a set of possible outcomes called the sample space, okay? And it's going to be denoted by a capital S in this course, but in another textbook that I'm working out of for a different class, they use a capital C, so we have to be a little bit flexible. But as long as we have defined the sample space and what letter we're going to use to denote it, that will be fine, right? So for us, we're going to use a capital S, but just be aware that, you know, it could be defined by some other letter. So the set of possible outcomes is called the sample space, and that's going to be a set, right? And so here, when we roll a die, S is going to be the set of 1, 2, 3, 4, 5, 6. Okay. Hopefully you're a little bit familiar with set notation. Okay, it's the set of 1, 2, 3, 4, 5, 6. Only one of those is going to happen per process, but those are all the possible outcomes. Okay, so here, the sample space for flipping a coin, right? So if we flip a coin, the sample space is heads or tails. Okay. What if you flip 2 coins? Okay, so if we flip 2 coins, the sample space becomes, so the first coin, I flip it and I could have heads. Second coin, I flip it, I could have heads. Option number 2, I flip the first coin and I get heads again to make room for having tails for the second one, right? Yeah. But I think you're missing one, HH, but I think you were just continuing mine. Good. Yeah, yeah, too fast. So then those are the possible outcomes for the first flip being heads, right? I could have heads, heads, or heads, tails. Or if I flip the first coin and I get tails, then I could have tails, heads, or tail, tail. Oh, that wasn't a very nice curly bracket there, but there we are. So now I have 4 possible outcomes. From here, right, I could figure out different probabilities, right? Because I'm going to assume that each of these occur with the same likelihood, right? And so if I want the probability of 2 heads, well, that's going to be 1 out of 4, right? We could even do something crazy, and I am getting ahead of myself here, but it's nice to have this to look at, right? What's the probability of getting at least one tail? At least one. So that could be 1 or 2. So here I have a tail, here I have a tail, and here I have a tail. 3/4, exactly, right? And so we're going to look at the possible outcomes that satisfy that criteria. So then it would be 3/4. Okay, so I was getting ahead of myself, but it's nice to see that you guys are on top of things. Nice. So to save us a little bit of time, what we're going to do is we're going to use probability notation. Okay, and so probability notation is written like this. So you use a capital P typically, and then of A, right? And I know you've seen function notation, f of x, right? So this is the same thing. You read it the same way. So the probability of A, right? And I've got it listed out here. So often we'll know the context of the process that we're talking about, right? And so there is a formula to get the n of the sample space. And now I'm completely drawing a blank on what it is. It could be, it's n by m. So for example, if you have this situation, what you would have essentially is heads or tails, and this is for die 1. And then you could have heads, tails for die 2. Right? You could even do, which would be, if you call this n outcomes and this m, then you would have n by m possible outcomes. Because you could alter it, right? You could have, these don't have to be the same things. You could have die 1, so you could roll a die, and then you could, hey, I called it a die. It's a coin. That didn't make sense. But everyone's on board. Coin 1, coin 2. But I could change coin 2 to be a die, right? And so then I would have 1, 2, 3, 4, 5, 6, right? And then I would have 2 by 6, so 12 possible outcomes. Or typically the main one that we consider is rolling 2 die, so then it would be 6 by 6, so 36 possible outcomes. Yeah, exactly. So if you have kind of 2 independent events, which we haven't talked about independent, but I think intuitively we have a pretty good understanding here. So what you can do if you wanted to list all the possible outcomes, and I have done that in the past because it helps me figure out and convince myself that my math was correct, right? And so in this case, I would join these up and say, well, that's the heads, this is the heads, tails, this is the tail heads, this is the tail tails, right? Adopt some sort of way to list these consistently, right? Okay, good. So we'll come back to that a little bit, but first I just want to talk about probability notation, okay? So if we know the outcome or the context, then we can usually talk about P of H, right? Which is implied that we're flipping a coin and the probability of getting heads is 0.5 or 1/2, right? P of T is 0.5, so 1 and 2 or 1/2. P of 2, it's implied that we're rolling a dice or a die rather. You can only die once. I use that all the time because 2 dice, 1 die. Right? You can only die once. A student taught me that a long time ago. It has really helped me. So the probability of rolling a 2 is 1 in 6. So we've seen that already, right? So here are some probability facts, and these you have to just remember, but also, so we'll talk about them in words, but then I say on your formula sheet, you're making your own formula sheet. But now that we're getting into more formulas, I'll post the one that I usually hand out. I forgot to do it. What didn't I forget to do today or for today? So I'll post the formula sheet that I usually hand out, but of course we're working in open book scenarios. So you should be working out your own formula sheet as we go, okay? Or just kind of cheat sheet, some sort of setup where you can find information quickly. So here below, it says how we summarize these facts on the formula sheet. But first, let's talk about what are these facts. So a probability has to be between 0 and 1, okay? And so a probability is the same as a proportion, remember? And they have to be between 0 and 1, okay? That's a fact. The total probability in your sample space has to add to 1, right? Why is that? Well, it's because your sample space has to list all the possible outcomes, right? And so if you've listed every single possible outcome, what's the probability of one of those happening? 1, right? One of those has to happen if the process is happening, right? And so if you've forgotten one in your sample space, then the probability of your sample space would be less than 1. So how we denote these is we use a general P of A, right? P of A is a placeholder for any probability. Oops. Hey. Okay. Trying to sneak it in here, but okay, there we go. P of A is a placeholder for any probability. Okay, so the probability, any probability is between 0 and 1, right? When would it be 1? Well, if it's the only possible outcome, which means it's not really a random process, right? If one thing exactly can only happen, then that's kind of boring, right? Because that's the sample space, which means that A would be the sample space, right? And so then P of S, now we're using that capital S, P of S is 1, so the probability of something in the sample space happening is 1. Here. Wait for it to copy. Come on. Good. So we're going to spend some time developing some terminology that we need. Okay, so 2 outcomes are disjoint or mutually exclusive if they cannot both happen at the same time. Now, what I like to do here is sometimes it's easier to visualize this. So we can visualize this with a Venn diagram. We can visualize this with a Venn diagram. And I think I hold off in the notes to introduce the Venn diagram, but I do find that it's the easiest way to visualize mutually exclusive. So what we have, a Venn diagram starts with a rectangle, and the rectangle is the sample space. So everything that could possibly happen is contained in this rectangle. So the rectangle denotes the sample space. Okay, all possible outcomes are in there. Okay, now 2 outcomes are disjoint. if they cannot happen at the same time. So if we have outcome A and outcome B, we can show them like that, right? So A and B are disjoint or mutually exclusive because there's no overlap, right? Maybe I'll do A and B are disjoint or mutually exclusive. And we use that term a lot just in regular language, right? Mutually exclusive. We don't usually say that things are disjoint, right? But mutually exclusive, we use kind of in regular language, right? So, oh no, those two things are mutually exclusive. Or maybe only I do, I don't know. No, I've heard people use it. So A and B are disjoint or mutually exclusive if there is no overlap, right? So that's how you would show it that they're disjoint, is by showing no overlap. Yeah. So here, we're talking about outcomes. This is where it gets a little bit tricky. So a singular outcome is rolling a 1, rolling a 2, rolling a 3, rolling a 4, right? Flipping a heads, flipping a tails. Each of those things are called outcomes. Usually, what we're more interested in is an event. Okay, so an event is a set of outcomes or a collection of outcomes. Okay. So for example, if I don't care if I roll a 4 or a 6, it just has to be one of those two possible outcomes, then the event that I'm interested in can be denoted by B, and I'll just put it here. B is the set of 4 and 6, right? Where 4 and 6 are each outcomes. Oops. But the set of 4, 6 is a set, well, it's a set. The set of 4, 6 is a set. Oh, right. Okay. So usually we're interested in a set of outcomes, which we call an event. Okay, good. Bring this in here. So here we have B is the set of 4, 6. We already wrote that because it was a page break. But then what we can do is, since 4 and 6 are disjoint outcomes, right? What do we mean by that? If I roll a die, right, one time, only one of the possible outcomes can happen, right? So here I'll explain. If I roll a die once, only one of the possible outcomes will happen. Only one of the possible outcomes will happen. Okay. So all the outcomes are disjoint. Therefore, all the outcomes are disjoint. So even if we're only interested in 4 or a 6, right, only one of those can happen, and so they're disjoint. So what we can do, and it hinges on them being disjoint, what we can do is we can find the probability of B is the probability of rolling a 4 plus the probability of rolling a 6, right? And so 1 in 6 plus 1 in 6 is 2 in 6. And we could have looked at the sample space and figured that out from there, right? But it's nice to have some sort of formula to kind of build it out to. But they're doing the same thing. Okay. Now, usually outcomes are not disjoint, right? And so, whoops. Let's grab all of this here. Now, this is where people tend to freak out a little bit. Hey, I don't know what the cards are, decks of cards. They're a mystery to me. How am I supposed to know that? I do expect you to have some common knowledge about a set of cards or a deck of cards because we do use them quite a bit. But if there are things like a full house, which I think is 3 and 2 or something like that, if there are things that you need to know specifically that I don't expect you to know, I'll tell you what they are, right? But here are some things that I expect you to know for cards. Okay. So here, I want this, come on, a little bit smaller. So common knowledge for a set of cards. Okay, so here's a full deck. First thing you need to know is there are 52 total cards. Okay. There are 26 red and 26 black. There are 13 of each suit. So diamonds, hearts, I can never remember. Spades and clovers, no, I know they're not called that. Spades and clubs. Maybe I should put it here. I'll need help with the black ones. Yeah, I think is it spade? It is. And then what's this? In Swedish, we just call them clovers. So it is clubs. Okay. Not so common knowledge after all. Here, these would be the diamonds, diamond, heart, spade, and clubs. Okay. So those are the suits. Okay. And there are 3 face cards in each suit. So these Jack, Queen, King are face cards. 3 face cards in each suit. That's pretty much all that we need in terms of kind of knowledge about cards. And then I can explain something from there, right? What's the, I might ask you something like, what's the probability of drawing 3 face cards, right? From a deck of cards? That'd be 3 in 52, right? Because it's just 3 cards out of 52. Okay. But let's consider a face card and a diamond card. Okay, so the cards that we're interested here in this scenario, face cards is just any one of these guys here. So we can count those. There are 3 by 4, so 12 face cards, right? Drawing a diamond. So now if I use a different color, maybe blue here, we can see, because I'm using these 3 cards, the Jack, Queen, King of diamonds twice, right? There's overlap. And so we can see that these events are no longer disjoint, right? So here, we see that these events are no longer disjoint, right? Because it is possible to draw a face card that is also a diamond. Okay. So what we want to know, and I think it's on here. Let's grab all of it. Why not? So what we want to find is the probability of a face card or a diamond. So if we want the probability of a face card or a diamond, right, we can't just add up those 2 probabilities. So if we look at the probability of a face card, right, there were 12 face cards. So the probability of drawing a face card from a well-shuffled deck, we always assume it's well-shuffled, is 12 and 52, right? Whereas the probability of drawing a diamond is 13 and 52, right? But what we've seen is that these 3 face cards that are also diamonds, are counted twice, right? So we've got the diamonds, and then we've got the face cards, and we've got that overlap. So how I think of it is we need to remove 1 overlap. Okay. So the overlap is 3 cards in this case, right? Which means that we could denote it by the probability of F and D, right? Because that's the overlap, is 3 over 52. Okay. And so what we could do is we could go through, because we have the sample space here, right? We have the sample space, and so we could go through and count, okay, there's 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There are a total of 22 cards that satisfy being a face card or a diamond, okay? So we know that the probability should end up being 22 over 52, okay? But what we're actually doing is we're saying that the probability of a face card or a diamond is the probability of a face card, oh, sorry, this one here, plus the probability of a diamond minus the overlap, right? So that's the general addition rule, and I'll bring in the official one in a little bit here, but I just wanted to point out that it has a name, and it's the general addition rule. So the probability of F is 12 over 52 plus the probability of a diamond, which is 13 over 52, minus that overlap of 3 over 52, putting us at 22 over 52. Right? It's nice because we've got that common denominator, so we don't need to make any adjustments. We can just add, subtract the numerators, and we're safe, right? But that's something to remember from kind of our math days. If you don't have a common denominator, you'd have to adjust for that. Okay? But usually, if we're talking about the same thing, it's not something we need to worry about. So come on. It's taking forever to let me copy it. Okay. So this gives rise to the general addition rule for non-disjoint events. Okay. On your formula sheet, we're going to have placeholders A and B. So the probability of A or B is the probability of A plus the probability of B minus the overlap between A and B. Okay. And so here, in terms of a Venn diagram, and what's nice about Venn diagrams is that the circles that we draw could be probabilities or just the outcomes. So it depends on what you want to talk about, but they are shown in the same way. So what we have is we could have a circle for A and a circle for B. Okay. So what we have is we could have the probability of A, which is all the outcomes in A over the total number of outcomes, right? And so you could talk about A plus B, but again, we've got that overlap, right? So we've got circle 1, circle 2, we've got that overlap. So if we subtract that overlap once, this overlap here, the overlap is A and B. So that's what we need to subtract once. We need one layer, right? Because it's part of A or B. Okay, so for us, when we talk about A or B, it's going to be everything in the A circle or the B circle or both. Okay, and that can be confusing. I know that's been confusing to a lot of people sometimes, but for us, A or B is everything in A or B or both. Okay. Yeah, because you'd be counting it twice. Exactly. Here, now we can go back and look at that special case where we started, because we were kind of just starting to develop all these concepts. But if A and B are disjoint, then they share no space in common, right? And so then we would say that the probability of A and B is 0, right? Because by definition, they cannot happen at the same time, right? And so then you would just be subtracting 0, but that's where we got that specific case for disjoint events, is that, okay, then we can just add up those probabilities and be fine, because the probability of A and B is 0. And I'm going to highlight this because I like to ask that question a lot. It's good. So what's fun is that if you have 3 of these 4 pieces of information, right? So this would be one piece, the probability of A or B would be one piece, probability of A 2, probability of B 3, and the probability of A and B is 4 different pieces of information. You could be given any 3 pieces of information and be asked to calculate the 4th, right? And so you could rearrange this formula and find the missing probability, right? So that's nice. Okay. Okay. Next thing I want to talk about is a probability distribution. Okay. I mentioned it earlier, there are situations where events don't have the same probabilities of happening, right? Different events are going to have different probabilities of happening. And so what we could do to show that is we could use a probability distribution. So a probability distribution is a table of all possible outcomes, right, which is the sample space. And in fact, they have to be disjoint outcomes. Okay. with the probability of each outcome listed below it. Okay, so here we have all the possible outcomes, and in this case, we're talking about rolling 2 dice. Okay, but from there, what we're going to look at is we're going to look at the sum of those 2 dice. It reminded the formula, and we need to integrate there. Yeah. We are not there yet. That's old chapter 3, new chapter 4, probably. I think I have to go back and confirm, but yeah, we are getting there though. We are. You can't wait to use your calculus. Yeah. It's actually very difficult, so we're only going to talk about it as like an idea. But anyways, because the normal distribution has a really nasty formula. Anyways, parking lot that. Okay, so we've got the list of all possible outcomes, which means that what we could do if we roll a dice or a die, and then we roll another die, what we could do is we could list 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and we could make a matrix, right, or a grid of the possible outcomes together. Now, what we're interested in is the sum, right? So there's only one way to get a sum of 2, right? There's 1 in 36 possible outcomes that give a sum of 2, right? 1, 1. Yeah. For a sum of 3, right? Remember, if in a 6 by 6 grid, there's 36 possible outcomes. And so here, that's where this 36 comes from. Six by 6 possible outcomes, possible pairs, I'll say. Okay, so that's where that 36 comes from. And then what you could do is you could go through and add up all the different pairs and find the dice sum. So now to get a 3, I could first roll a 1, and then I could roll a 2, or I could roll a 2 and then a 1, and either way the sum would be 3, right? And so that's how I get the 2 out of 36. Okay. Notice how the probabilities are increasing until I get to 7, a sum of 7. And then it's decreasing again, but it's actually symmetric around 7. In terms of kind of gambling, right? A sum of 7 would have the lowest payout because it has the highest probability of happening, right? But it's also your safest bet. Right, so this would be your safest bet of 7, and then as you move in either direction, and it actually doesn't matter which direction you move in, right? Getting a 6 and a 6 is just as hard as getting a 1 and a 1, right? Just as hard, or just as low probability as getting a 1 and a 1. Right. But if you want to play it safe, but you still want to gamble, I don't know, then you would bet on a 7. And then if you want to kind of step it up a notch, you could go for a 6 or an 8, and then 5 and a 10, or 5 and a 9, blah, blah, blah. Right. And so this table here is what we call a probability distribution. Right. And it just outlines the probability of each outcome. Okay. So a probability distribution is a list of the possible outcomes with corresponding probabilities that satisfies 3 rules. Okay. The first rule is that the outcomes listed have to be disjoint, right? It doesn't make sense to talk about a sum of 2 or 3, right? Because as one thing, because there's only going to be one sum. Kind of a bad example. Typically what happens is if we're talking about income categories, that's kind of the most common one that I've seen there be errors in, is 0 to 20,000. But then instead of going, and if we're keeping it in thousands, if instead of going from 21,000 to maybe 25,000, they just go from 20,000 again. So then there's that overlap of 20,000, which is happening in both categories, right? And so that would be non-disjoint outcomes, okay? First thing we check, are each of these things disjoint? Yes, in this case, of course, they are. Second thing we're going to check, and it all goes back to just general probabilities. Each probability has to be between 0 and 1, right? And that just goes back to that original statement that the probability of a general probability of A has to be between 0 and 1. And then the probabilities must total 1. Right, and so if I go through, I've got a common denominator of 36 here. So if I go and I add up the numerator, I should get to 36 out of 36, right? I'm not going to check that because I know it's true, but you can go through and confirm. Okay, but I have an example where we're going to go through and we're going to check some of these things because it is going to be important to recognize a valid probability distribution. I guess, oh. Let it catch up here. Oh, hey. So now we're going to have 3 distributions for household income in the United States. And so only one is a valid probability distribution, right? So we've got A, B, or C are our options. And we're going to go through and figure out which one is the valid probability distribution. So first thing we're going to do is we're going to check, right? Are the outcomes disjoint? In this case, the income ranges are in the thousands. And so 0 to 24, okay. Moving over to 25 to 49, good. There's no overlap there. And then 49 to 50, okay, good. 99 to 100, all the outcomes are disjoint. Okay, so kind of option number 1 or criteria number 1, check. They're all disjoint, so that's good. So one of these can be a valid probability distribution. If it said 0 to 25, 25 to 49, 49 to 99, 99 plus, those would not be disjoint, right? Which means none of these would be valid probability distributions because it failed that first criteria. So if we look at option A, remember the next thing we check is to make sure that probabilities are between 0 and 1, right? And so I just scan this whole table and I just want to make sure that everything's between 0 and 1. And because I have this negative, right, B is not an option. Right? Can't be a probability distribution because it has a negative probability. All the other ones are between 0 and 1, so that's good. So then the next thing that we check is they have to add to 1. So the sum of the probabilities, if we go through, is more than 1. So if I go through, let me just grab a calculator here, and I add up 0.18 plus 0.39 plus 0.33 plus 0.16, I get 1.06. And just to confirm, I'm just going to add these up, but I think they add to 1, or I know they add to 1.28 plus 0.27 plus 0.29 plus 0.16 puts me at 1. So because this had a sum of 1.06, it can't be A. And so the only one that satisfies all the criteria, all 3 criteria, is C. Okay. Therefore, C is the only valid probability distribution. I underline valid because it's something that that people get confused by a lot of the time, because a common question that I ask is, I give you a probability distribution and I ask you, is this a valid probability distribution, right? And then you have to go through these steps and you have to tell me why it is or why it isn't, right? Or I might say there might be a probability missing, right? Then if it was missing, if it was missing 0.16 here, let's say that was just a blank, and I asked you to find the probability, the missing probability, in order to have a valid probability distribution, then you would have to know that, okay, they have to add to 1, and so it must be 0.16, right? So there's lots of things that we could do here around this valid probability distribution. Okay. So, like I said, there are instances where the probability of an outcome is maybe different for different outcomes. And maybe I'll crop this. Wait. Here. So I can blow it up. So what we're going to talk about is expected values. Now, expected values are also the mean, right? So the mean of a distribution is the expected value. Okay. So what we've seen, right, is that, okay, we're assuming that the probability of each outcome is always the same, right? And so we can find the mean of some outcome or some variable X where the probability varies across X, right? And so the mean can also be called the expected value. And so sometimes in kind of higher stats textbooks, instead of using the mean or kind of X bar or mu, usually it replaces mu, we use this notation E of X, right? So the expected value of X. And so what we say is that the expected value of X is the sum of X times P of X. Right, and so it's the sum of the outcome X times the probability of X, probability of outcome X. Okay. Come on. So here, what it says, right, is we're going to have some outcome X, and I'm going to use lowercase x and capital X in this case interchangeably. And I know that's confusing, but that's just something that is going to happen. So X has outcomes 0, 1, 2, 3. So it's some random process where it has outcomes, possible outcomes 0, 1, 2, 3. We assume that these are disjoint because they cannot, only one of these can happen, right? And I'm also giving you the probability of X, right? And so this is a probability distribution, And what we're seeing is that the probabilities of these are not the same, right? And so we see that 1 is most likely to happen out of any one of these 4 outcomes, right? Whereas a 2 is the least likely to happen with the lowest probability. Okay, so now we've got this kind of wonky distribution, probability distribution for X. And so that's okay. Let's just make sure that it's a valid probability distribution, right? We already said, okay, these are disjoint outcomes, good. Each of these probabilities are between 0 and 1. And if I add them up, 0.2, 0.4, 0.6, 0.7, 0.3, 1, good, okay? So it's a valid probability distribution. And that's just something, you know, you should be checking each time. So what we're going to do is we're going to think of it as 0 happens with a probability of 0.2. 1 happens with a probability of 0.4. 2 happens with a probability of 0.1. And then 3 happens with a probability of 0.3. So what we can do then is we can take the sum of each X times its probability, right? So 0 has a weight, and it is a weight of 0.2 exactly. Hey, great minds think alike. It's exactly like weighting. So 0 has a weight of 0.2, whereas 1 has a weight of 0.4. So then what you do is you can make a new column here of X times P of X, if that helps you, which is going to be 0, 0.4, 0.2, and 3 times 0.3 is 0.9. I always get confused with decimals, I guess. Just confirming. Okay, good. So then the sum of these is 0 plus 0.4 plus 0.2 plus 0.9. Right, breaking up that sum, the summation just into some multiple parts here. So 0 plus 0.4 plus 0.2 plus 0.9 puts me at 1.5. Which means the value that I'm expecting to have is 1.5. Notice that that's not actually one of the outcomes, but the expected value is if I look at it an infinite number of times, right? If I consider this, then the value that I should be betting on is 1.5. So you'd have to choose between 1 and 2 because those are the only outcomes, but the mean of X in this case, right, is 1.5, 1.5. I do want you to take a step back and think about the mean in general, right? So if we think about X bar as we know it, well, that's going to be the sum of X over N. How does that relate to the expected value of X? Well, if we think about X times P of X, right? So now if I copy this X and P of X, what I'm going to have, if I have outcome 0, 1, 2, or 3, just looking at the same thing here, if they each have the same probability now, right? Just to mimic this over N, this would be 1 in 4, 1 in 4, 1 in 4, 1 in 4. So then what if I have, and maybe I'll remove this line and put a line here instead. What if I have X times P of X? Well, that's going to be 0 times 1 over 4 plus, oh, sorry, not plus yet. We need that sum first. 1 times 1 over 4, 2 times 1 over 4, 3 times 1 over 4. And if I add these up, so now I'm going to add the summation here because I'm lazy. then I'm adding these up. With the common denominator of over 4, right, I can pull that outside of the sum, because if I'm adding, I don't add the denominators, I only add the numerators. So if I'm adding these up, then I get 1 over 4 times the sum of 0 times 1 plus 1 times 1 plus 2 times 1 plus 3 times 1, right? But that's just going to be, when I'm timesing by 1, right, this just becomes 0 plus 1 plus 2 plus 3, which is the sum of x. And, oh yeah, is it 1 plus 2 plus, oh, sorry, 1 plus 2 plus 3 divided by 4. Well, that's a fluke, 1.5, but that, yeah, I guess it happens. And maybe there was a reason I wanted to show you guys, but anyways, fluky. Okay, but so this X bar that we're used to calculating, so when we're used to calculating an average, we are technically using the sum of the x's times p of x, right? We're technically using this, but because the probability of x is just 1 over n, right, then we get the simplified version. So x bar is the sum of p of x times p of x, where p of x is 1 over n, right? Okay. So that's something to keep in mind, right? When we're doing these expected values, we're actually not changing the game that much. We just need to adjust for the weightings, right? Whereas here, when we have equilikely outcomes, then we don't need to make those adjustments anymore. Okay. Good. Let's see if I have a little tidbit that we can end on. The complement of an event has already sort of come up. Remember the video, half do or half don't? Both. Because one of those options, if half do is A, then the probability that half don't is also is the complement of A. So we've already sort of seen it, but here we are. So the complement of an event is all the outcomes when the event doesn't happen. So it's going to be the sample space without the events that we're interested in, right? So if we roll a die, right? And so here I'm going to add that S is 1, 2, 3, 4, 5, 6, right? If B is the event 4, 6, so 4 or 6, I don't care, then what we do is we denote the complement of an event by a superscript C. We can use a prime, and sometimes I'll use a prime because I get lazy, but we don't want to confuse those with derivatives, for example, because derivatives do come up in statistics, of course. And so we don't want to get confused. So we should be using a superscript C, right? And so this denotes the complement So it's all the outcomes that didn't happen, right? Or don't happen in B. So if we have the sample space and B is 4 or 6, then the complement of B is 1, 2, 3, 5, right? Everything except for 4 or 6. So the complement of B can also be denoted by B prime and is read not B, or you could even slip up and say B prime. The context will make it clear which one you mean, if you mean a derivative or the complement. But just to play it safe, we can read it as the complement of B, or usually I'll just shorten it to not B. Okay. Not B, or the complement of B. Okay. But usually I'll just read it as not B. So in general, what we have is the probability of the complement of A is going to be 1 minus the probability of A. Okay. And so if we take a step back, we understand this intuitively, right? If I told you something scary like the probability that you will pass this course is 70%, what does your brain do? What's the probability that you don't pass this course, right? That would be the complement of passing the course. Well, your brain takes the 70%, converts it to a decimal 0.7, and then takes 1 minus 0.7, and then you're at 0.3, and then your brain just goes 30%, and then it cries just a single tear. But that's what your brain does, right? And so if I told you, yeah, but that's impressive, right? So if I tell you something, it has to be something important to you, right? The probability that you will win the lottery is, let's make it something crazy like 0.4%. Remember, I'm talking about percentages because often when we're speaking, we talk in percentages, right? I don't know. I'm making this up. Don't take my word for it. But the only way to win is to play. So I don't know. Right? If you don't play, the probability of winning is 0. So what did I say? 0.4%. So then your brain takes it, probably converts to the complement first. And I'm just talking about how my brain works. I would complement it by saying 100 minus 0.4 is 99.6%. So the probability of the complement would be 0.996. What a mess. But anyway, so we have a really good understanding of this setup here, right? That the probability of the complement of something happening, so the opposite of something happening, is just 1 minus the probability of it happening. All right. So if you have any questions, because I'm all out of time, a priori is in reference to Bayesian statistics, and that's not my field. I'm a frequentist, and so I'll have to look it up, but it's like you have some prior knowledge. But anyways, we'll probably touch on it just a smidge, but not much. Bayesian statistics. Oh yeah, if you have any questions, let me know, and I'll post the minute to keep watching that video that I made available for Friday. Or you could watch it today if you wanted to keep the good times rolling. Anyways, if you don't have any questions, I hope you have a wonderful week, and I'll see you next Tuesday, I guess. Weird. I'm gonna stop this here.